This presentation showcases capstone work from Michigan Tech students in the Formula SAE Enterprise program. Each year, our team designs and manufactures a single-seater Formula-style race car and competes against 100 teams from around the world. The competition takes place every May at Michigan International Speedway and consists of several static and dynamic events. Our team is organized into sub-teams including chassis, composites, electrical, powertrain, business, and our recently launched EV sub-team. Some capstones taking place within our team this year include the aero rake, which measures the pressure gradient across different planes on a vehicle. We also have vehicle simulation, taking various input parameters to simulate vehicle performance. Next, there is the F26 brakes to plan and validate the brake system for next year's 2026 competition vehicle. And then the F26 electrical system is planning a new electrical system for next year's car that includes an ECU and sensor package. In this video, we'll be taking a closer look at the F25 aero package, advanced powertrain development, and EV drivetrain controls capstone projects.
This is the F25 aero package. Some of the rules are that we cannot design outside of some of the boxes you see on the right. To be legal for our competition, you must stay within these boundaries to compete.
So some of the goals for this F25 aero package is to improve on some of the weaknesses of the last car. So that would be reducing the aero sensitivity. So as the vehicle changes position, making sure we keep a consistent amount of downforce. We want to reduce the package weight by about 40%, which equates to about 20 pounds. We want to incorporate pressure and load sensors so that we can get real numbers associated with our aero loads. We want to have a buffer to all of the aero bounds to make sure we are legal. And we want to have a range of different aero configurations to make sure we can meet the different needs of each event, and then make sure we have ground clearance at all vehicle attitudes so that we don't contact the ground.
For the F25 aero package, we utilize NX as our main CAD software to design each aero component. We then import those components into Star CCM Plus, which is our main CFD software. We utilize Star for 2D optimization to generate optimal slot gap, overlap, and angle attacks of our element stacking. We then take that into 3D half-car simulations to see the performance numbers the components make. We then take the CFD pressure map from Star and import it into Hypermesh as our FA load cases to verify the structural integrity of our components. We then utilize Fusion as our main CAM software to generate G-code of our molds.
The F25 aero package consists of a front wing, rear wing, diffuser, and side aero, and at 22 meters per second, we produce 1,180 newtons of downforce and 442 newtons of drag. For the F25 aero package manufacturing, we utilized a CNC router for fast machining and ensuring our parts were representable to CAD. We utilized 3D printing for inner wing supports and mold manufacturing. And then we're projecting a 50% loss in total mass from last year's aero package.
So we've got the advanced powertrain development modeling. We've got Xander, Mikkel, Mitchell, Carl have been working on this. So for the overview, we've got kind of four main topics. We did control strategies, a flow bench, some modeling, and a carbon fiber intake fold. From the control side of things, we got three main topics here that I looked at. I got the launch control, traction control, and anti-lag. Launch control helps you get steady launches every time. Traction control makes the car easier to drive at the limit, and anti-lag keeps you at peak boost all the time.
We also developed an airflow bench to help quantify improvements in airflow. This will help us collect data for combustion modeling and also help us calibrate our GT power models.
We also made a 1D model. The goal of this was to predict our powertrain performance changes. So as we change intake manifold, exhaust manifold, cam phasing, or other things, we can see actually how that is going to affect before it happens. And that allows us to prioritize what technologies we put before others. We correlated that model to expect experimental data, which is shown here. So we took a large amount of experimental data throughout the year, and we used that to kind of improve the model. So the model make prediction. We'd use experimental data to correlate the model. And using that, we were actually able to prioritize components such that we created a 20% increase in peak power year over year.
Into a carbon fiber intake manifold, our goal is to save some weight in our intake and improve our power output. Carbon fiber will be strong enough for the job, and we've proven that it will not hurt our intake air temperatures, so we're confident moving forward. We're going to manufacture it starting next semester with a two-piece 3D printed split mold using standard 2x2 twill weave, which will provide the strength we need. and a high temperature epoxy that will withstand our high intake air temperatures due to our artificial atmosphere with the turbocharger.
This is the EV drivetrain control senior capstone project. So the overall goal of the project is to get a electrically based running vehicle. So a big proponent to that would be simulating our expected loads and parameters needed for a safely functioning and operating car. And then that we are also able to put together with our research what we need for future projects.
Here are some rules that we're currently using for SAE. So these are the main ones that we had to keep in mind. There's a lot more, but this is a good baseline that we started with. And using those rules as well as the current materials we have in the shop, which is an electric motor and a motor controller, we designed a good drivetrain system that could be used on a competition-ready car. And first, we started off with a PMDC simulation. So we essentially used this as like a black box model where we were just modeling power in and power out. We weren't really worried about the inside or the guts of the system at this point, but this got us a lot of really good metrics in regards to performance and efficiency. And more so than that, it was able to prove that our drivetrain system in regards to the cabling that we designed here, as well as the future power source we will be utilized, is 100% official and is going to be able to necessitate our system. And we do have a PMAC model we will be using, but this is in current development. This will be utilized a lot more for the controls aspect.
And alongside our work with research and planning ahead, we've been able to, with the help of other mechanical engineers at FSAE, put together a to-be running electric vehicle system using an older chassis, a 5 horsepower motor we have on hand, as well as a frequency drive and a motor controller. This is mostly to validate that our simulation does work and we know what we can get out of it, even though it's not perfect.